Welcome. Having seen the general formula for finding shear stress in beams in the last lecture, let us now study the shear stress distribution for rectangular beam sections in particular. Let's draw a rectangular cross section with width B and depth D. We show the neutral axis and the arbitrary layer at a distance of y from it. The general shear stress formula for an arbitrary layer is given by S times AY bar over BI, where S is the maximum shear force acting at some section along the beam's length. AY bar is the moment of area above the arbitrary layer about the neutral axis. B is the actual width of the arbitrary layer, and I is the area moment of inertia of the beam cross section. This equation is simplified to get S over 2I times d square over 4 minus y square. This formula can also be derived using integration limits. Here we find that the shear stress is a function of distance y of the arbitrary layer from the neutral axis of order 2, meaning that the variation is parabolic. If we take the double derivative of the shear stress with respect to y, we get a negative sign, meaning that the curve obtained is of the maxima type with respect to the zero shear stress line. For maximum shear stress, we equate the derivative of shear stress with respect to y equal to 0, for which y is found to be 0. That is, the maximum shear stress is obtained at the neutral axis. The value is found to be 1.5 times S over BD. S over BD is also the average shear stress in the beam cross section. Hence, maximum shear stress equals 1.5 times the average shear stress. We draw the shear stress distribution diagram besides the beam cross section and label the values. Note that the shear stress for the top layer is equal to 0 since the area above the top layer is 0, and the shear stress for the bottom layer is also found to be 0 since the distance of the centroid of the area above the bottom layer from the neutral axis is 0. If, for example, the width B equals 10 millimeters, depth D equals 20 millimeters, and maximum shear force equals 10 kilonewtons, the maximum shear stress is found to be 75 megapascals. In the next lecture, we shall study the shear stress distribution for circular beam sections.